This is lab 1 for physics, constant velocity. So in this lab, we're tracking the motion of an object, in this case a tennis ball, as you can see here, that is traveling at a nearly constant velocity. And we want it to be a constant velocity so that we can then apply Newton's second law. And by having it near constant, we're basically saying that no new forces or F net are being influencing our system. And as you can see in this graph right here, it is fairly linear, which is saying essentially that we do have a very constant velocity and don't have any forces acting on the tennis ball or our system throughout the test. So using the information that we gather from tracker and our video, the actual data, we are then going to take the velocity and take all the information that we've gathered and use it to make an ideal model that we can compare it to that actually has completely no outside forces acting on our system. So using tracker, able to find the rate at which the tennis ball is moving, total distance being around half a meter, as you can see here, and the total time span being 0.901 seconds. Using that too, we take the first 2 frames of the actual footage, which is why we have 0.033 seconds for the initial velocity. So this is going to be the velocity that we want to compare it to and use for our model, so that we have what would be an ideal velocity that it shouldn't change if there was no outside influence on our system. So using or changing the variables over here, like the ball's mass, which is 0.56 kilograms, and changing the initial position vector to be the one that we have in the actual video, being around 0, 0, 0, and then the initial velocity, which we're going to want to keep the same because no outside influence, right? To be around 0.609 meters per second, which is what we were saying in the previous slide. So then for the calculation loop, we have t, like a while loop running for the time frame that we're working with, 0.901 seconds. And as you can see, the F net is going to be a vector of 0 because we don't want any outside forces in our system. So that's going to stay the same. And then as you see below it, the ball velocity, the formula is Newton's second law. And since the F net is actually just a 0 vector though, we will have a constant velocity that doesn't change, and the ball's position, as the formula underneath says, will just go at the same rate over time. And we take that information and we compare it to the actual data in this next slide. So as you can see, our model is perfectly linear, showing that there's no outside forces and it's completely constant, while our actual data, graphed by the red dots, actually drops off at the end a little as the expected rate from natural forces that we didn't want acting on our system that are naturally going to happen. So likely the disparity comes from some sort of friction or maybe some sort of gravity that comes with the tennis ball, especially because the ball has the fuzz and all that things that could cause it to slow down. And with that, you could probably have shortened the interval that we were studying. So as you can see, around 0.6 seconds is when you have that drop off and have that disparity. Had you had the frame maybe shortened a little bit, it would have been nearly linear with it, showing that we did replicate to a certain extent no outside forces on the ball for that time interval. Also showing that Newton's second law, that if you can minimize the amount of forces acting on our system, that your object or whatever is in motion is going to stay in the same motion that you'd expect it to be.